Welcome, everyone. Thanks for coming. For everyone that is not doing Journey to the Universe today, so if you don't teach into kindergarten kids, we can listen to talk about same level of astronomy.
Right, yeah.
So it's a pleasure to have here TC that is visiting from Taiwan, and she's going to have a full year in Hawaii. So if you want to talk with him, you can take the chance today or anytime the next few months.
Just next door, yeah.
Yes. He's a East Asian observer. TC did his PhD in Durham University, correct?
No, Hawaii.
You did your PhD in Manoa.
Yeah,
correct?
Manoa, yeah.
Manoa, and then you moved to Durham.
That's right, yeah.
And then you moved to ESO,
Yeah.
and then you became staff
Yeah.
at ASIEEAA.
Yeah, it's good. In
he's-
Taiwan.
TC is an expert on everything that is dusty and unknowingly bright in the millimeter wavelength,
Right.
but really obscure in optical and near infrared. But is now moving to appreciate also other lines like Lyman alpha finally
And quasars.
and quasars. But the stage is yours. Please go ahead.
All right. Thank you, Emma, for the introduction, and thank you for having me. So, like Emma was saying, I'm Chen-Chou. No one just go by CCC. That's what TC comes from. I'm a staff at AGIA, and then visiting for the year at JCMT. And I knew Emma from a conference, and I knew that he's here, so I thought, well, I should come here, talk to people here, because I do multi-wavelength studies for galaxies, massive galaxies in general. Okay. This is essentially based on the survey. I'll go into details later on, but these are the people, especially Fabrizio here is my partner in crime. We started this survey when we were postdocs at ESO, and now it's been almost 10 years. So it's been a long coming journey that I really appreciate. And we also got to work with a number of excellent students that contributed to this project. Okay. So today is about dusty view of protoclusters, but I thought I should probably introduce a bit broader about my general science interests, and more or less boils down to this evolutionary track that you might have seen before, especially focusing on massive galaxies. Massive meaning 10 to the 10th solar masses or above. And there's this schematic picture that people propose that want to have Big Bang, and then the cosmic web started accretion gas into dense nodes. And then that's when you trigger mergers, and that's when you have a lot of star formation goes on in a very short period of time. And if you do star formation, once you have a lot of star formation, it'll produce a lot of dust. And then that's why you got dusty galaxy at its face. And then, interesting enough, some of the gas, some of them goes to the softening region, some that actually goes to the black hole. So they affect the black holes, generate a lot of feedback, and obviously also grow the black hole itself. So they have black hole accretion as well as consumption of the gas in star forming regions, and that coordinatedly, having the feedback and consume all the gas. And then that turns into quasar galaxies that you see. So this is a time, by the way, this is about redshift 6, redshift 2, this is cosmic noon, what we call it. And this is redshift 1 and local galaxy, massive ellipticals. The timeline here, obviously, is very general. It's based on the accretion history of black holes as well as star formation densities that we see from surveys. But just take it as a grain of salt. These are general pictures that we understand about evolution of massive galaxies. And I'm interested in this phase because, as I said, this is when most of the stellar mass of the massive ellipticals that we see in the local universe grown. This is essentially the assembly phase of both stellar mass and black hole mass, essentially. And I've done a lot of work in the past, essentially in my career, focusing on here. But today the talk will be mainly focusing on this transition, or we call it maybe coevolution phase, that between dusty galaxies and quasars, in particular their environments, how they correlate with each other, and how they co-evolve with each other. Okay. So the correlation between dusty galaxies and quasars, I mean, so far we know, from JWST study, from ALMA studies, in the core scale, within the halo scale, we see a lot of these evidence from redshift 0 all the way to redshift in epoch randomization. But then actually in the larger scale, there's evidence for that as well. This is based on a work in the Herschel era, which is quite some time ago, but then it's still, the results still valid. What people do is that they cross-correlate the dusty galaxies that are found in the Herschel maps. These are hundreds of degree square scales, by the way. And then also cross-correlate with the SDSS quasars about cosmic noon. When they do the cross-correlations, here's the signal they found. This is a cross-correlation signals, essentially how correlated are these two populations in the y-axis. The stronger, obviously, then you have more signals. And this is essentially the separations of the two pairs between dusty galaxies and quasars. Okay, so you can see their signals from here. This signal is essentially coming from the quasar themselves, because this is the PSFs of the Herschel. So you see signals from the essentially point spread function level, and that's suggesting quasars themselves actually emit some of the far rate, which is not too surprising. Maybe they are low in luminosity, but they are there. They're signals. What's more interesting is that if you look at the larger scales, this is essentially an arc-minute or even 10 arc-minute scales, essentially corresponds to about megaparsec to 10 megaparsec scale, physical scales. You see emissions also coming from the cross correlations. So that suggests dusty galaxies should be around quasars at that similar scales in a statistical way, right? This essentially from cross correlation. Well, my job is try to go and deep do the surveys to see how are they actually distributed and what's their correlation, what are the relationship in more details. So they coexist at cosmic noon, but we could also do autocorrelation functions to find out what are the halo masses they are residing in. So 2-point correlation functions will essentially measure the number of access pairs per given separations of two galaxy pairs. Okay, so you can imagine if you are residing in more massive halos, you're gonna have more massive pairs. More access in the pairs, and that's pretty much the concept. I'm not going to detail the measurements, but I'm just going to show you the results. The product of the autocorrelation function is essentially R0, the characteristic length that can produce an X amount of access pairs. So the longer of your calculation length, the higher the mass of your halos. That's on average, by the way. Okay. So these are dusty galaxies. And this is based on what we did back in the time, 5 years ago now, with one of my students. And then the gray scale here, they're all quasars. And these curves are essentially the correlation length at the given redshifts at different halo mass. This is 10 to the 14, this is 10 to the 13, and all the way down to the 10 to the 10. So what you found is the quasars, at cosmic noon, they occupy, in the dusty galaxy, they occupy the halo mass of about 10 to the 13 solar masses. That's at cosmic noon. And if you do evolution of lambda CDM, and these galaxies are expected to evolve into essentially present day clusters, which is 10 to the 14. So they are tracing on average protoclusters, not every of them, but on average collectively. They should be tracing protoclusters at cosmic noon. Okay. So that bridges us to the protocluster studies in order to understand the convolution between dust galaxies and quasars. Theoretical perspectives tells us, now also confirmed by observations, is that protoclusters are large back in time. This is n-body simulations for halos, and then this is present time, how the cluster looks like. They are compact, about 1 megaparsec. But if you trace it back, those member galaxies back in time, you'll see that they're expanding their footprints in the megaparsec and 10 megaparsec scales. And then back in the time, as expected, you expect to see a lot of star formation. This is what this figure shows. This is redshift, by the way, and this is where the cosmic noon is, what we're talking about. This is when essentially the peak of the stellar assembly of the cluster themselves, that's where the epoch, the time that they form most of their mass. And the bottom figure is also important. It shows that the fraction of star formation stellar mass that's actually within the core of the protocluster. This is the core, and this is the whole footprint. So as you can see, model predicts that although there's a lot of star formation going on in protoclusters, most of them are actually not in the core. They are in the outskirt regions on megaparsec scales. So that highlights the importance of not only just studying the core with JWST and ALMA, maybe we need to go broader scales in order to study the full protocluster growth. This is another angle trying to highlight this, the footprints of protoclusters. This is essentially the radius of the size of the protoclusters went back in time from redshift 0 all the way to redshift 7. And the red dashed lines highlight the core region, which is always about 1 megaparsec all the way to cosmic noon, whereas the true extent of the protoclusters actually goes all the way, this is megaparsec, all the way to almost 10 megaparsec. Essentially, again, driving the force argument that you need to go wide, not just in the core. So in the picture of a protocluster, again, in the central regions, it's great in ALMA, very deep studies and JWST. But then in the outside regions, ALMA essentially cannot probe so much of area. And then that's why we use Scuba 2 for this case. Herschel used to be able to do it, but I think Herschel mostly they are too shallow at cosmic noon in order to probe more typical galaxies that's in this epoch. And these Scuba 2 surveys can help us do that. And with that motivations, these are the questions I tried to go through. I don't know how much time, if I can, go over all of them, but these are the things I'll try to go through. First, I'll introduce the survey and try to answer the questions: how often dusty galaxies are, located around quasars at cosmic noon? We have a sample that's hosting Lyman Alpha Nebula, which I'll go into the details later on. And we have a sample about 20 to 30. So we're actually doing a survey. And how are they distributed? Are they more centrally concentrated, or are they more evenly distributed? Or, do they trace filaments? Any structures we can see, beyond only the cross correlations. That's the first part. And the second part are going to the follow-up observations. That's in particular using ALMA, try to get lines from these member galaxies and try to understand spin axis and how that relates to the filaments that they are tracing. Okay. So as I said, this is a sample that we have about 20. And this plot shows essentially the targets compared to the parent sample. This is the UV magnitude, absolute UV magnitudes. This goes to brightest. And then this is the size of the Lyman Alpha Nebula. So just to give you a sense, these guys are, we call the enormous Lyman Alpha nebulas. They have Lyman Alpha size of about a few hundred kiloparsecs, just in Lyman Alpha. They're huge. Okay. So we map a range of the Lyman Alpha size as well as the UV magnitudes for the quasars. And I said that includes some of the samples from ELAN, we call the enormous Lyman Alpha Nebula. And then some of the, if you're in the fields, there's the Quasar Museum, is essentially a Muse survey of, I think, 100 quasars at cosmic noon. And we select some of them. So these footprints are Lyman, they are all Lyman Alpha, and these are all like almost 100 kiloparsecs, few tens to 100 kiloparsecs. And then there's also a Muse large program that targets redshift 4 quasars. So we span not just a wide luminosity range, wide size range for the Lyman Alpha Nebula, also some span of the redshift from 2 to 4. So we can start to search for any correlations between the properties of these quasars and dusty galaxies. So quickly showcase some of the Scuba 2 maps that we have. This is 4 enormous Lyman Alpha Nebula. If you're in the field, you probably heard of it: the Slug, Jackpot, Fabulous, and Mammoth. As a reminder about the scale, the ELAN is actually at the very center. This is the quasar. And we're able to probe, this is megaparsec scale. This is about 5 no, almost 10 arc minutes, by the way, across. So that's surely 10 megaparsec at cosmic noon. So we're able to probe our scales. The first thing we try to do is do number counts, very simple. You count galaxies. Obviously, you need to do proper modeling to take away the completeness, adding bias and all that. But we did all that with the modeling. And then you compare to the blank field counts, and then you try to see if they're overdense. And that's one way, statistically, to say whether they are dusty galaxies around quasars. So you have the results, and this is what the actual results look like. Like I said, we do modeling. These are the measured data points. And then what we did is that we inject phase sources into a pure noise map. And then essentially, we do the source extraction and do the number counts in the same way that we do for real data. And we try to reproduce the number counts level that we see. So in order to reproduce this number counts we see, we need to inject a source model like this, which is the blue line. And then what's the field? This is the field in the dash gray. And this is the extracted source counts if we're using a blank field number counts model. So it's obviously, in a significant way that the dusty galaxies are overdense compared to the field in this area. Not just one, we have, I think, 4 of them measured in the same way. So as you can see, the blue, which is what you want to look at, is always higher than the dash gray, which is the field. So that's it. And evidence that dusty galaxies are around them. And overdensity factor is about 2 to 4. Right.
Just showing my ignorance here, but when you showed the map before, the slug nebula actually looks to have only like 3 or 4 galaxies, while the other one looks like crazy over there.
Yeah, so that's why in the model. So this is essentially misconception about the number densities, that the noise level is actually not even. So you really need to do like proper modeling in order to get the real source counts. And the ones that we marked are the brighter ones. But the counts, you can actually go much deeper than the source extraction you get. So the ones that you get and the brighter end. So here we go. The source number that you see on the map are the brighter ones. But once you do proper modeling statistical way, you can actually probe the counts much deeper. So you're right. In the brighter end, slugs is actually much lower in the numbers. So not just simple counting number of sources, but
There's a bunch of faint.
Yeah, exactly. A bunch of faint stuff that you don't actually see. Yeah. Thanks for the question. Any more questions?
Remind me what the solid blue line is?
The solid blue line is the input counts model in order to recreate the observed counts that you see in the real data. So effectively, these data suffer from completeness issues, flux boosting issues. Once you correct all that, the intrinsic underlying count model are supposed to look like this, the blue ones.
Yeah, I was trying to understand why it didn't match the data points.
Yeah, because
it's because the
flux boosting mostly. So the resolution of JCMT, it's good, but not great. It's about 10 arcseconds. So once you go deep, you start to hit confusion limits. So you have essentially a signal blended with multiple sources underneath it. So that's why models comes in to take out the flux boosting effects. Right. Yeah. Okay. Cool. Thanks for the question. Here are more counts, more fields, because we have more than 20, right? So I mean, all of them, most of them, about half of them, more, look over them. Some of them they don't, indeed. So there's a scatter of distributions of dusty galaxies, which is what we expected. You don't expect dusty galaxies to be always around quasars, but on average, that's why you need a survey to do a sample. If you care, these are overdensity factors we measure from 1 all the way to 6. There's one overdensity of 6 that we've been following with JWC and ALMA. Try to. So now the basic message is very simple. I mean, you have a lot of dusty galaxies around quasars. But as I said, we did sample a wide range of properties of quasars. we try to find correlations of these overdensity factors with the properties of quasars. And the short answer is no, we didn't find any correlations. So if we plotted overdensity factors as a function of redshifts, so as you can see, it's flat. And we try to plot it as a function of the UV magnitudes, and it's also flat. Well, that's just suggesting that if you think of the overdensity factor as a trace of the halo mass. So if you remember the autocorrelation function that I mentioned before, quasars and dusty galaxy, they'll trace similar halo mass across a very wide range. And this results actually agree with that. Essentially, the overdensity factor trace halo mass, and they all lie into similar halo mass range. And that's why we see not much of correlation here. Okay. But interestingly, although there's no correlation with the quasar properties, but dusty galaxy do tend to locate the region that's closer to the quasars. So we split the number counts by different separations from, this is about, I think the units here are megaparsecs. Yeah, these are megaparsecs. So within 1.5 megaparsecs, and then so on and so forth. You see the highest overdensity factors. These are all density factors, and this is the random, which is 1, no overdensity. You see the highest overdensity in the central regions, and outskirts start slowly to decrease. Interestingly, it didn't go to 1 yet at the furthest out distance, suggesting that maybe even in the outside of our footprints, there's still more dusty galaxies don't probe yet at this region, at this moment. But they are, more closer. The closer to the quasars, you see more dusty galaxies. Or essentially, maybe there's inside out growth. You grow the protocluster in central first, and you start to propagate out. In addition to that, because we have a large map and we have quite a number of them, we could actually try to find if they're preferred to locate in certain directions, presumably tracing filaments. So that's what we did. This is you want to look at the maps that's in the central panels. These are 2 fields, by the way, 2 fields. And then the central panel just shows super 2 sources across the 2 different fields. And like I said, because the noise of the super 2 map, they are not uniform. So we need to, they are deeper in the central regions and the shallow in outer regions. So when we try to find the preferred directions, which is essentially try to do a fit to see if they align. And we need to account for the completeness, essentially. This is what the size of the points are for. And we did it in 2 ways. And this is the probability density distributions. They are not flat. This is essentially a simple message. They prefer to trace some angle of the filaments. And interesting enough, because we have Lyman alpha in the central regions, we could compare the major axis of Lyman alpha with the direction that's traced by dusty galaxies. And we found alignments for at least for systems that have single quasars. So these are the results of the single quasar. Essentially, you compare the filament traced by dusty galaxies and also the major axis of the Lyman alpha. And we found for source systems that have single quasars, the Lyman alpha align well with the filaments that's traced by dusty galaxy on megaparsec scale. Somehow, the megaparsec scale structure talks with the Lyman alpha nebula structure in a few hundred kiloparsec region. So maybe they are tracing all the same thick filaments in order to explain this finding. But for ELAN, the enormous Lyman alpha nebula, which normally come with a multiple source in the region, like multiple 2 quasars, quasar plus multiple AGN in order to power a gigantic Lyman alpha nebula, we do not see a clear alignment. So more like this, they are misaligned with the filaments. That's in my megaparsec scales. So maybe that's suggesting that because there are so many things going on with the ELANs, they are more chaotic in the central regions. So which is why you don't see a clear alignment with the megaparsec scale structure and what's going on with the central quasar.
I may be jumping ahead.
Yeah.
But what you're saying is that, so that if you assume that the Lyman alpha is powered by the quasar,
Mhm.
the quasars implying like opening angles that illuminate the gas.
Mhm.
But you're saying that also the quasar itself knows about the alignment with the cosmic structures. Is that
The alignment, the distribution of Lyman alpha and lambda correlate with the quasar opening angle as well as the gas distribution.
yeah? But it's the two are degenerate. No, you don't know which one.
Yeah, we don't know which one is which, so we don't. Yeah,
So in principle, you can say also.
I wouldn't push that far. It's possible if you think about they're all residing in the same filaments. They are
I mean,
similar.
the most simple alternative is that it is not the quasar powering the Lyman alpha nebula.
Oh, gravity,
It's more gravity or stuff from
resonance scattering. Yeah, it's possible. That's an
and then
issue.
you lose the correlation with the quasar itself, so you
Yeah.
actually constrain the powering mechanism indirectly.
Yeah, and that's possible because we do. I'll come back to this. We do discover star-forming galaxies within these nebulas. So I mean, that's a big topic. I think is still under discussion. Probably more expert on this about what's actually powering these Lyman alpha nebulae. But yeah, I don't know the answer. What I can tell is that they align to some systems, and they don't align with the ones that have multiple sources that's within the central regions. Cool. We try to understand more about this. If multiple systems do not have Lyman alpha that's not aligned with the megaparsec scale structures. So we extend the survey to actually look at a sample of quasar pairs. They are rare, but we find them in SDSS. And we do it again with scuba 2 maps. So this is one example. There are 2 quasars, and these are Lyman alpha emissions. By the way, they are the central region is the scuba 2 map again. So large scale, zoom in, smaller scale Lyman alpha, and we try to do the same exercise about the alignments. Here are the maps. Again, they are overdense, even more so than the single quasar system. So if you look at the counts here, this is a blank field counts, and the red ones is the quasar pair. So they are even more overdense than the single quasar and the quasar that we see in the previous version. So maybe because they are 2 quasars, they are even more dense structures they are tracing. That's one possibility. And the key is that there's no alignment. Okay. In this case, these are 7 fields that we look at. And then you probably couldn't see it from behind, but you look at the dark line in each of these panels. They don't really align with the quasar pairs. The quasar pair themselves, they have directions, right? And as well as the Lyman alpha. Quasar pair direction is blue, and the Lyman alpha is the dash blue. So you want to look at the visually, the dark black line with the blue lines. So you see some of them are even perpendicular with each other. So they don't align as well. We have a sample, so we can actually do statistics. This is the separation angle between the filaments as well as the Lyman alpha major axis. The separation, essentially the angle. You see from system that have only 1 quasar, so 1 AGN, there's axis amount of, if you look at the green, compared to the rest of the colors that have multiple systems, the green ones tend to be more aligned into that structure. So they are more closely aligned to this schematic picture here. The gray is the filaments, dusty galaxies, quasars, and somehow the Lyman alpha is also aligned with the filaments themselves. For the multiple systems, as I said, you have more quasars, more chaotic environments, maybe in the central regions, centered around the quasars, which is why you don't see much of an alignment. Maybe they are just misaligned, tilted. Really depends on what's going on in the 100 kiloparsec regions within the halo scale. Okay. In addition to look at the directions, we can actually stack all these distribution together. Sorry, these are each individual maps with the dusty galaxy distribution, right? We have a lot of them. So we can rotate, align them, and then stack them. And that gives us a width of the filament. And this is what we did. This is the probability distribution. We align all on the x-axis. You can start to see the density distribution of these sources. And then they actually have a width that's similar to what you expect from a filament. We can actually measure the characteristic width of these filaments, and it's about 3 megaparsec, with some error bars, give and take. But I think this is an interesting try that we haven't seen a lot that's been done before. Interesting enough, this width is sort of consistent with model predictions. So models, n-body simulation model with dominated halos, they actually look at the filaments and filament width, and they try to plot the filament width as a function of. So filaments have thinner filaments, as you can see, and thicker filaments. And 3 megaparsecs are about the same width as the thick filaments that's traced by massive halos. So massive halo trace thick filaments, and dusty galaxies are part of that thick filaments, which is why you see this about 3 megaparsec scale width. Seems to be consistent with the pictures that we see. Some uncertainty here, but it seems to agree with that picture. Okay, a brief summary about our SCUBA 2 survey. We found almost ubiquitously in a majority of them, they have quasars, they have dusty galaxy around them. There's not much of a dependency of overdensity factors with quasar properties. Maybe they're consistent with the picture that the two systems occupy a similar halo mass range, which is about 10 to the 13. And the filament structures can be traced by dusty galaxies. And then the filament structure actually align well with the Lyman Alpha Nebula within about 100 kiloparsec scales, traced by filaments of megaparsec scales. And then we are able to try to measure the filament width that is currently consistent with model predictions. Okay, I'm done with the first part of the talk. Any questions? How much time do I still have? Go to the second. Okay. All right. Here we go. Now we have, SCUBA 2 is great, but they are 2D. Everything is projected. So we want.
Sorry, I have a question on the first part. So what about other tracers? So tracers of protoclusters, and then also tracers. So like if you normalize the dusty star forming galaxy overdensity by the total number of galaxies, do you see a differential increase in these environments?
Normalize the number of dusty galaxies.
By like, let's say LBGs, for example. So the incidence of dusty star forming galaxies, is that higher in these environments?
Yeah, so that's something I was hoping to collaborate with people here, is to try to get LBGs and LE measurements in these fields, which is we don't have for now. It'll be great to do that. Other studies have found mixture of results, right? Some of the fields they found dusty galaxy trace similar structure as LBGs and LEs, but some they found a very different distribution. Again, this could be halo mass dependence. You have more massive halos maybe tracing one structure, and slower mass halos like LBG LEs, they're tracing more like walls or even voids around protoclusters. But for our fields, exactly. That's what we try to do as well, to try to get a multi-wavelength picture perspective of the same field with a large sample. I think that's the difficult part. And with spectroscopy follow, it's going to be a lot of work for sure, as you probably know. Yeah.
And what about for protoclusters, like other tracers, for example, massive galaxies or variety of other?
Yeah, people use, for example, if you want to know, they are more mature, you want to use X-ray. X-ray gives you protocluster mass. You can use SPT to use SZ effects. Yeah, there are many ways, or you can use red colors to select overdensity of quasar galaxies, red galaxies. That's what people tried to select before. Also emission lines, also absorption lines, right? There are a variety of, and I don't have a right answer of how do they compare results. What I do know is that quasars are probably tracing the massive end of all these structures. And then I think it needs a bit more thinking about how do we put all these things together. Yeah, there's some great work, surely, with other fields and selections, radio galaxies as well. And now with JWST, the redshift 6 quasars, you see all these structures around them with the GRISM surveys, right? You know, it'd be interesting to see if they actually trace filament structures, although they might be smaller footprints.
But those are more on like 500 kilowatts.
Yeah, exactly. So again, so you know, it'd be worth, and maybe we can do a GRISM surveys going to larger scales, multiple pointings to get the filament structures.
You haven't pointed SUPA to at like a massive galaxy over density or a different type of system that a quasar.
Yeah, we did. We tried to point at radio galaxies, and we also find over densities. The radio galaxy survey is called Ragers. The interesting part there is that you have radio jets, some of the systems. So you can actually study the distribution relative to the radio jets. Here we study correlation with the Lyman Alpha Nebula, right? Here you can study the correlation with radio jets. And what we found is the dusty galaxy prefer to avoid the directions of the radio jets. Maybe there's some feedback effects there that's heating up the halo gas and it stop the star formation for those things. Yeah, I mean, it's a growing field, right? I mean, different samples are coming together and trying to put together all the pictures to try to make sense of it. But it's all very important. Right? Any more questions? All right, follow up. So we had Alma try to get CO line emissions from all these samples. We did a survey of almost 80, 90 sources, but we only got 15 detections. I won't go into the details. If you're interested, let me know. But I'll just focus on the ones that we have detection for. This source, this field's OA19. If you remember, this is the one that has most over density.
Just to be clear, you don't have detection nor in the continuum nor in the line, or you don't have detection.
We have continuum,
Okay.
but
So
you
they are
don't
real
have the line.
sources, but
They are real sources, probably.
not in the windows of line, or the line is too faint.
Yeah, so we went back, when we write a paper, we have to explain this, why it's so low detection rates. A is we didn't go deep enough, because we designed the line measurements based on the lines that detect in the field. So in the field galaxy, they don't report, they don't have a field survey, whole survey CO, and they don't report non-detections. Right, so you're having this detection bias of the bright stuff. So one, we didn't go deep enough. Two, we didn't go wide enough in spectral coverage. Because these sources, we only probe maybe 50 megaparsec scale in radio distance, but these sources could be 100 megaparsec. So that's 2 seconds. Three, would be more interesting is that the galaxy here, they are different than the field. They may be more fainter, so we don't see them. So there are a number of reasons. But it's also hard to prove because it's hard to go back to the text, say, hey, give me 50 hours more. Let me prove it. So we try to spin it in other angles, which maybe I'm happy to talk about in the future. But anyway, this is the field that have the most over density factors in the SCUBA 2 surveys. And this is also the field that we have the most line detections. So I mean, we have 5 or 6 within this again, quasars here, 100 kiloparsec scales and megaparsec scale distribution. And clear line detections. As I said, we design the experiment, go to the depth that's comparable to the field galaxy. So it's not surprising that we detect lines that's comparable with the property that's comparable with the field galaxies, right? On the high side, you know, it's not surprising. But anyway, they feel, so the blue are ours. This is line luminosity, line width, and infrared luminosity. And these are selection. Essentially, you don't see things here. You never see things here with the proper analysis. And the orange ones are the ones you see in the field. They occupy a similar locus. So you can conclude that there's not much of an environmental effect here. You know, dense environment, they don't affect CO properties much on megaparsec scales. And these sources, we can do SED fittings. So they have Herschel maps, they have ALMA, we have SCUBA 2. So we can actually sample pretty good range, especially with the one with Herschel, from the peak all the way to the Rayleigh-Jeans tail. Okay, so we can actually get those properties. Dust temperature, as well as the emissivity index, which is the slope of the very genus. Long story short, they all consistent with the field galaxies. So these are our data points. In the background, they are field sources. It's infrared luminosity, dust temperature, follows similar trend, and this is beta, so about 2 roughly. So again, not much of environmental impact on dust properties. We have fine for SC feeding, so we can have stop motion rates. We have gas mass. By dividing that, we get depletion time. Something that galaxy people look at is the depletion time. And then again, you don't find much of a difference. Our examples here, this is a field extrapolation. They agree. And also you can look at the gas to dust ratio, which is about 50. They are dusty galaxies, so normally people assume 100, but here they are high. So, but this is not unexpected. They are consistent with the field sources. But there's something that might be different in the dense environments, which is the gas fraction. As I was saying, we're trying to do multi-band follow-up. We try to do near-infrared to get stellar mass. We don't have that yet. So we try to derive something assuming a simple dynamical equilibrium, and assume some dot matter fraction of these dynamical systems. And we're able to divide. I'm happy to talk about details about here, but on my papers, I propose that once you have line width, you assume size, which is measured in some of the field sources, and you assume dot matter fraction, and you have a line luminosity, you can get gas fraction. A bit complicated, but it's all can be boiled down into this plot. Y-axis is here, and then the x-axis is the luminosity. And then assume the fixed dot matter fraction, go into that. But once we believe that's probably true for the average for the massive sources. So this is why I only compare to the massive galaxies, dusty galaxies and quasars. The diagonal lines are gas fraction. So it's 100%. So essentially, meaning that you have the same amount of gas, molecular gas, and with the stellar mass, that's 100%. 10% gas is that you have 10% stellar mass, that's in molecular gas, and 1%. And the blue is the field as well as our measurements. As you can see, they are more aligned to about 100%, which is not unknown. People know that dusty galaxies, they have comparable amount of molecular gas mass and stellar mass. They are massive systems. But the ones that's closer to the quasars, which is the solid red ones, as well as the quasar themselves, which is the orange ones, they start to migrate to lower gas fraction. Okay. So this is an interesting trend. You might wonder, what if you plot gas fraction versus distance? And that's what we did here. This is the central is the quasar themselves. And then you have dusty galaxy that's around quasar. The gray area mark the virial radius of the quasar, which is about a few hundred kiloparsec. And these are megaparsec. So you do see some trend of evolution. If you go to megaparsec scales, they agree with the field. But then once they get down to the virial radius, they start to see lower gas fraction. It's a very interesting mimic to what we found in the Virgo cluster. You see distance versus gas fraction. I mean, not necessarily corresponding. These are galactocentric radius normalized probably by the cluster radius. But you do see that within we go to the closer to the central region, you start to deplete gas. And there's also other samples in the cosmic noon that people start to find when we go to the closer to the center of the mass, you start to see depletion gas. Okay. I'll quickly go over why is that, and we have some evidence try to explain why you have lower gas fraction. This is one of the fields that we have ALMA observation. This is by the way, this is now a Lyman alpha, which is about 100 kiloparsec. ALMA footprint is right here, and we detect this continuum. We detect two quasars. This is the Slug Nebula, and then we also find a dusty galaxy that's within the nebula. This is the line from the quasar no light detection from companion quasar, but you have an additional source, clearly both in continuum and line, that's within the footprint of the Lyman alpha nebula, which is the collapse map. And coincidentally, there's Keck observations. There are two slits. One's here, and this dusty galaxy right happened to be at the cross section here. So we got free Lyman alpha long slit spectra from Keck by coincidence. The blue slit, covers the quasars right here and dusty galaxies right here. You see, sort of a connected Lyman alpha, what you sort of expect, because this is within the Lyman alpha nebula. But the interesting thing is the slit 2 is that from the dusty galaxy and all the way to the systemic of the quasar, central quasar, you see this long extended tail of Lyman alpha from the velocity of dusty galaxy all the way to the systemic of the companion quasar. So maybe there's some gas stripping that's leaving out the dusty galaxy and slowly got slowed down by the halo and then meet the velocity of the companion quasar. This is about 100 kiloparsec in separation. And then this is what it's looked like compared to Lyman alpha nebula. So we think that this cloud could be tracing this tail here of the slug. We can try to calculate the mass of this tail. I mean, it's very rough, so bear with me. Order of magnitude. Oh, I showed this already. But then you can try to calculate that with the assumption of area and proton mass, hydrogen mass fraction, which you can always get from the Lyman alpha modeling, and also the column density of the cloud. I mean, it's very rough. But once you do the exercise, you found the strip gas is about 10 to the 9 solar mass. Now, is that enough to account for the depletion of gas that you see from the ALMA observations? The answer is no. This depletion is about 10 to the 10. So it's about order of magnitude more than you see from the strip gas from Lyman alpha. So we think that stripping is probably there, but it's not enough to strip out all the gas that you see from the observations. So it could be strangulations. There's another possibility is once you in the massive hot halos, is that strangulation means that the gas don't go into the gas anymore. They are strangled. So left with the gas that they are available to consume out. So we did rough calculations. These sources about 100 solar mass per year. And they may be, I didn't go time to have gone to the detail, but we think they have the crossing time. The dusty galaxy entered the halo in the last 100 million years. Can you do that calculation about 10 to the 10? Very rough, but it's fitting to that picture. So we think stripping is there, but you need strangulations to do that. How am I doing with my time? 10 minutes?
2 minutes.
Okay.
If you don't want questions, 5 minutes if you want.
All right, let's take questions for now. From this third part, before I go into the spin alignment, which is something that's work in progress. I like feedback on. All right, I guess that means I can go ahead. So, more follow-up. Hold on. Here we go. More follow-up. Now we have detection of CO. Then we just want to resolve it, and so we have higher resolution, about 0.5 arcsecond. At cosmic noon, that's about 3 or 4 kiloparsec. If you want to get the physical scale, it's not great, but it gets start to resolve. You can start to get rotation per se. We can get redshift and blue shift side of the galaxy. So this is the first follow-up. You get a line, and it was not resolved for this example. But now we have more follow-up with better resolution. Now we start to see the rotation, blue side and the red side. Still very crude. You can do some modeling. That's what we did. We ran 3D Barolo, which is what people normally do nowadays. Try to get inclination angle, position angle, velocity dispersions. This is honestly, this is one of the best example, which I show here, that you can constrain. But most of the sources, they are not very well constrained in the probability distribution. Okay. but I think we are more confident about the spin direction, where the things spin, because we see red and blue, right? So we should be measured better on that part. So we measure the spin axis for all the 15 sources. No, actually only 12 deliver. So we measure 12 of them spin axis. And if you still remember that we collapse the filaments and get the filament distribution of the width. And we want to do the same exercise, then we want to put on the galaxies that we measure that have spin axis. This is the filament on the x-axis. It's all light down, it's all corrected, and we make sure that the spin angle is correct relative to the filaments. And you see some tendency of parallel, this direction is the spin axis, right? So this is like that, the right-hand wall. And then you see, if you plot the distribution of the angle versus the filaments, we don't have a lot of sample. You kind of see by model. We did some statistical tests, is 2 sigma compared to random. We need to grow a sample size, but this is the first try, so bear with us. But interesting enough, recently, there's H1 survey that had similar idea. They discovered this is the mighty survey in the Cosmos field. This is the Cosmos field, but along that, in the foreground, obviously, this is a 0.03. Cosmos is in the back mostly. They found a filament. These are all like directions they measure from the spin axis. And we can do similar exercise. And voila, they have similar sort of bimodal distribution as well. Blue is ours, and the hydrogen galaxies is theirs. Statistical tests, the case test says these 2 samples are the same. Very high confidence. Why is it bimodal? I don't know. The model says the galaxy should tend to be perpendicular to the filaments. So these are 2 simulations, hydro simulations from Eagle, and this is from SINBA. The way to read this figure is that this is theta, now theta is cosine theta. And how they define is that above the vertical axis in both figures, above that they're parallel. So spin axis is parallel to the filaments. Below that, they're perpendicular. Okay, so you see that both they predict the spin axis should be perpendicular. Not strictly perpendicular, because this cosine theta is 0.4. And this dynamical range is very narrow. So I wouldn't read too much into their models. But in a general sense, they should be perpendicular. And there's also mass dependency. Whereas more massive galaxy, they are more perpendicular than the lower mass ones. Once you go to the 10 to the 9, it starts to become in a parallel regime. Okay, there's mass dependency. So this is related to the tidal torch theory. I don't have time to get involved into that in more detail. But model should predict that there should be one way, not bimodal. What we think it is that maybe it's our fault. We only study the 2D projections. Maybe you want to do 3D. And this paper, they did that. And then, although in 2D, they see bimodal, but then once you correct for 3D, you start to see numbers that are closer to what model predicts, a cosine of 0.5-ish. Okay. So maybe we are similar things. They are perpendicular to the filaments. Anyway, this is really the first try for the cosmic moon. Hopefully we'll get more data and verify this. All right, I think I'm coming to the end. I'll leave the summary here. Thank you.
Questions? Too clear. Too clear.
Too clear.
So what fraction of the galaxies of these 12 that you have some sort of kinematic information on look disturbed, or otherwise seem to have some sort of merging activity or torquing activity?
Yeah, there's 1 or 2 sources that you don't see clear rotation sign. You don't see red and blue. So maybe that's one sign. There's also another source. Once we resolve it, we resolve into 2 sources, which I didn't show, but there's one example of that.
So one example you showed there, the upper sigma looked like it was pretty low, like the sigma looked really good, looked like the sigma not hit by saw correctly.
Swing.
Yeah, I think you had a better plot on the previous slide.
Yeah. But these observed sigma though, these are not corrected for the beam smearing yet.
Okay.
So we really need to do the model. You have 2 or 3 resolution beam, so I wouldn't read too much into detail about the results of the modeling. The error bar probably is going to be huge. Yeah, V over sigma is a hot topic recently for galaxies. We'll try to do that and see. We'll try to push for analysis. But we'll see what we get. Yeah, it's one thing we could discuss, whether there's a V over sigma environmental dependency of V over sigma. Yeah. But yeah, I mean, we'll probably write another proposal to do more follow-up to get 0.2 oxig.
Nice talk, TC. So in terms of the population of the dusty galaxies, do you want to go wider? Do you want to go deeper? Do you want higher angular resolution? Do you want more clusters? What's
All of them.
all of them? Yeah.
All of them.
Choose one.
All of them. All of them. I think Scuba 2 is great already in terms of footprints. We see some evidence that you might have more in it, even outside of the Scuba 2 footprints. But I would like spectroscopy, to be honest, because 2D is great, but you're limited to what you can really learn. In 3D, obviously, you can learn a lot more. Yeah, so spectroscopy would be great. Both ALMA and also maybe in the OIR region, you can also complement the lower mass galaxies and high mass, so you have a general big picture about these structures. Yeah,
Maybe something we could do with on-chip spectroscopy.
that's what I'm looking forward to. We want to build a 50-meter. It's called Atlas. We want to have millions of spectra, but that's 20 years away. But that's the goal. Or do a slow type of survey, hopefully.
More questions? There is time for one last one. We reached down there. I can ask one, just to finish. For all your ALMA data, you also have follow up with the central quasar.
Yeah. Is there any correlation between the property of the central quasar and the alignment alpha arrow then?
So in the first round of follow-up, we should have, but we actually didn't observe all the quasars. We only have one, which is why I show. But then in the quasar pair system, we did put that in, and we just take that data and we're in analysis. But like I said, what I was telling you, this triple system that Eileen found, now we have a dusty galaxies right next to it. And then it's probably going to be more that we can learn. Now we have, I think, 7 quasar pairs. We can have a statistics. So that makes it quadruple system with dusty galaxies and quasars within 50 kiloparsec. We don't know how to explain that.
Okay. TC was going to be here for the next 11 months. So if you
Happy to
for a
collaborate.
question.
Yeah, I just wrote a proposal with Gemini because you guys are here. We'll see how it goes.
So let's thanks.
Yeah.